Hey everybody, today we're going to be talking about how to homogenize a non-homogeneous partial differential equation. First of all, you can see that this is just kind of a simple example. We have a like Laplace equation with a source term um, where the domain is from 0 to 1 for any time greater than 0. And you can notice that the boundary condition, or one of the boundary conditions, is non-homogeneous. So in this process, we're going to have to homogenize that as well. So the first thing to remember when dealing with PDEs always is that PDEs are really a summation of building blocks. So like in the last video when we were doing the separation of variables, and we were splitting U into a G of X and H of T, those were examples of us kind of defining building blocks to our actual solution we're trying to solve. So in a similar way to that, the first step in this is we're going to have our solution variable equal to a steady state solution added to a transient solution, which in this case will be noted by omega. Then when we plug this value back into here, we're going to get it to look like this. Over to this value right there. So let's scroll down a bit. So then what we're going to end up seeing is that we have this is equal to this. Okay, and then using something called the superposition principle, we can define this here because if you were to separate these into two different partial differential equations, the solution of these two partial differential equations will end up adding up to our overall solution. But this allows us so we can then solve these two equations by themselves. And you'll notice that if we were to add these together, it would just give us back to what we originally had. So then when we go down, we're going to solve the first one first, which is du ss dt is equal to d squared uss dx squared plus 1. But because it's a steady state solution, and we said that it was only dependent upon x, we know that this goes to 0, and we're given this. As you can note, this is a ordinary differential equation, and as such can just be solved using our solving techniques that we learned back in differential equations. In which case we can have -1 is equal to us double prime, so you got negative x plus b is equal to uss prime, which becomes -1/2 x squared plus bx plus c is equal to uss. Okay, So if we go back to our boundary conditions, we'll note this one right here, that x equals 0, du dx is equal to 0. It is important to note that this is the u quantity. However, by just saying that the derivative of this quantity is equal to 0, so we impose this condition, in which case we have negative x plus b. We can determine that b is equal to 0. And then if we go back up here again, and we impose this condition, that USS is the component of u that provides this u equals 1 at x equals 1, in which case we have USS is equal to 1, which is equal to negative 1/2 x squared plus c. And this is at x equals 1. So then that would be negative 1/2 plus c is equal to 1. So then c becomes equal to 1.5. Okay? And then this gives us USS is equal to negative 1/2 x squared plus 1.5. Okay? So this is our steady state solution. So now when we apply the things that we considered, which was this and this, to our initial boundary conditions, we can now find new boundary conditions for our transient solution, which, if you remember, the transient PDE looked like this, right? So then you could, yeah. But then we don't know what the boundary conditions or the initial condition is for this one, because we haven't yet incorporated the changes that we've made. So if we look back at here again, at these conditions, we have du dx equals 0 at x equals 0. And that is really du ss dx plus d omega dx is equal to 0. So if we look at du ss dx, how we had defined it before, right here we define that as equaling 0, which in turn made the du dx need to equal 0, or d omega dx also equals 0, in which case this becomes one of our new boundary conditions for this transient portion. And then we can do the same thing for our second boundary condition, where we had u is equal to 1 at x equals 1, and that becomes USS plus omega is equal to 1 at x equals 1, which we know at x equals 1, we had 1 here, right? Because if you put 1 here, you get negative 1/2 plus 1.5 plus something would equal 1. So if we do the algebra there, we can see that this will also equal 0. So u will equal 0 at x, or omega will equal 0 at x equals 1. This will give us our second boundary condition. The other important thing to notice is that we also need to account for the change in our initial condition. So we had at t equals 0, omega is equal to 1, or sorry, u is equal to 1. So now we have at t is equal to 0, you have USS plus omega is equal to 1. Of course, we already have the value for USS, which is negative 1/2 x squared plus 1.5. Omega is equal to 1, which when we solve that, we'll get omega is equal to 1/2 x squared minus 1/2 at t is equal to 0. In which case now we have an equation that is homogeneous with no source term with a initial condition that we can solve here. And then from here, you'll just use your separation of variables that we covered before, or that I covered previously in an earlier video, to figure out what your omega component is, and then you'll add that to the steady state solution that we've already solved to figure out what your final u is. It is important to note that in the solving of this, you might get a solution that is still in terms of n. That is perfectly okay, depending on what your other conditions are. Anyways, so yeah, so hopefully this was helpful. Again, if you get stuck at this part of how to proceed, I recommend you look at my old video or previous video on PDEs in order to see how to proceed from here. Anyways, thanks for watching.